Hi, welcome back to the lecture series on GPU architectures and programming. So, we will just start with a small errata of our coverage in the last lecture. So, one was regarding this chain rule. So, if you just check, we have been earlier talking about this y's in vector notation, but since we are having a summation here, that would mean we are doing a summation over the components errors. So, that should essentially be small yi's. And also continuing further, one other issue would be like here in the chain rules derivative, since we are considering capital Y's which are the vectors, so the summation would really not be there, right. If we remember that we have already discussed how we do the forward pass and how the derivatives related, how to compute the derivative of the loss function with respect to the weight matrices W and W prime, and how those are really used to figure out this value of the derivative, that is in the second stage it is this x transpose delta 2, where I can also have the delta 2 expressed as the value of delta 1, then W prime transpose, and then the activation functions gradient at those values, right. So, with this I believe we had already discussed what was a backpropagations rule, that in the backpropagation pass you recompute W prime. So, you reevaluate using your computation of delta 1 and delta 2, you are essentially recomputing W prime to be W prime minus A transpose delta 1, and then you are also using delta 2 to figure out what would be the updated value of W. So, that would be W minus X transpose over delta 2, like that, right. So, like this was our summary, that whenever you are doing the feed forward propagation, it is a series of linear and nonlinear transformations, essentially all in matrix operations, and during the back propagation you also have a series of such transformations, again that those can be, but they start from the output layer towards the frontal layers. So, that is why it is back propagation, and we want to do all those things using the parallelism that is available in the GPUs, right. So, with this background, in case you are interested in building a deep learning library, so that would mean your library should have to support the following things. That means it should provide constructs like how somebody can easily specify the neural network architecture, what kind of efficient routines I can implement as part of the library, so that I have feed forward, back propagation and gradient computation, these features available, right. So, they should just be available as function calls when I am accessing the when I am building a complex neural network architecture and going to implement it for doing all these computations, right. So, of course, and using these routines, I will like to build high level routines for doing the neural network training as well as testing process, right. Moreover, as we can understand that the library will like to exploit HPC resources. So, all the operations have to be implemented, these operations of feed forward, back propagation, gradient computation, they have to be implemented using suitable data parallel languages like CUDA or OpenCL or something else, and it should really be configurable. That means, once I tell that this library should be running in this kind of an architecture, it should be explored to figure out, well, let us say I am trying to say that I want this library to run in a CPU GPU system where the GPU has this many SMs, this many SPs and all that, then I should follow the standards we discussed earlier, that how to really define the architecture, how to write your program in such a way that all the variables get configured based on the architectural resources that are available, right. Something like this is already available for us. Many of us have already heard about these popular deep learning libraries like TensorFlow and Theano, and they essentially follow all these standards and discussions we have just done, but at the high level they provide an abstract view of the neural network. They provide what we call as a computational graph abstraction, which helps you to encode the different parameters and the connections that should be there in a very complex neural network architecture. So, we are just trying to provide an abstract view. On the left hand side, suppose you have this multilayer perceptron like we have discussed earlier. So, you have the input, that input x vector is getting transformed with W, right, and then you get something called this intermediate value, that is the z, which gets transformed with the activation function, you get something called A. These are all intermediate values that you are computing. Then again you have to do further transformation on A using these weights of W prime, that gives you G, and on this you apply the final activation function F again to get the output, right. Like I mean we have to understand that this is the neural network computation which this architecture will do, and we like to encode it in the form of a data flow graph. So, that is a usual way in which a computer scientist likes to encode his computation. So, it is basically like you have nodes which kind of represent the input data or some transformation that has to be done, right. And then the output of the transformation is provided to another node where some further transformation will be done, right. So, as you can see on the right hand side we have an example computation graph where we have two nodes x and w which provide the input data, and this data flows following these edges to this node where I have computed the value z, and on the and this node is labeled like this, f of u comma v is u v. So, essentially I am trying to say that this node performs the following transformation, that is it takes the left and right operands and does a matrix multiplication, right. Then the output will flow to another node, I call that output as A, right. So, this is dependency is further captured by this arrow from node Z to node A, and here how do I really get A? So, the computation that will provide me A is again denoted here using this function f of u. So, I am just saying that the function takes whatever argument, let us call it u, the output is sigma of u. So, sigma is a activation function here, right. And then again this output A and some other input node W prime, these two inputs flow to give me another output G, and this output is derived by considering the corresponding function labeling, where I am saying that this function is f which takes again two parameters and does their multiplication. So, again A and W prime gets multiplied to give me G, and then again I have the another activation function giving me the final output which is O. So, the convention we are following here is every node has the data representation, and following the dependency edges the data flows to an output node, and the way I get the output node is by a suitable function transformation, and the function is provided as a label, right. So, this is how we are trying to signify how the computation, how the data flows through this transformation network in the form of a computation graph. So, better to say is just another way to represent it where we are making the dependencies explicit. So, just to summarize, this is a graph that will denote the functional description that I require for the computation. A node which has got no incoming edge is a tensor, or it can be a matrix or a vector or a scalar value. A node which has an incoming edge, it is a function of the edge's tail node computation. The edge represents a data dependency between the nodes, like we saw earlier. The edge just tells me that the data will flow in the direction of the edge, and as long as the data is not available in the input nodes, the edges leading to some output node, there the computation is not going to happen, right. A node knows how to compute its value and the value of its derivative with respect to each incoming edge's tail node. Now, that is important. So, every node knows how to compute its value, and that is known by the associated function. Like here this node knows that it has to apply this multiplication function, right. And also it knows how to compute the value of its derivative with respect to each incoming edge's tail node. So, if asked, this node can compute the derivative of z with respect to w. Okay. Now, this is the next thing that we will use. So, considering j as the loss function, again let us recall that we have this computation going on. So, x multiplied by w is going to give me z, we then compute f of z which gives me a, we use a and w prime to generate g, then we compute or apply f on g to get o, and finally, we using o I compute the loss function, right. And as we have been discussing that every node knows, since the dependency of the node is always I can figure out the dependency by looking into the incoming edges. So, for every node I can compute its derivative with respect to the variables in this incoming edges corresponding nodes, right. So, given z, I can figure out dz dw, or tracking backwards, let us say I want to compute some overall derivative, I can follow the derivatives chaining rule as we know, and using the chain rule I can compute each of the individual derivatives and compose them. So, we will see an example, but before that all I am trying to say here, since I have this kind of a dependency, for every node I can figure out, let us say from j to o there is a dependency, I can compute del j del o. Similarly, I can compute del o del g del w prime, del g del a del z, so on and so forth. So, what happens in the forward computation for the computational graph? So, it simply loops over each node in the topological order and computes the value of the node given its inputs. So, as we know that the topological order is nothing but a linear representation of the node ordering of a directed acyclic graph, right. So, essentially I can compute a topological order for any such graph, where the node which is dependent on some previous node, that dependent node will come later on in the order, right. So, following the topological order, I can simply loop over the graph and compute the corresponding outputs. And then for backward computation, what am I supposed to do? If you remember what we did in the neural network, you just went back from the output layer to the input layers, right. Essentially the same thing. So, you loop over the nodes in the reverse topological order, and you want to for computing the derivative of the final node with respect to each incoming edges tail node. That means, you do this computation, you compute del j del o del g and like that. So, this is how I can do the forward and backward computation, but how does that really help? Our overall objective is to compute this, right, del j del w. So, as you can see, we have been discussing earlier that I can follow derivatives chain rule, and since each of these expressions would be available to me, because I have these dependencies for each node, I know their values and all that. So, I can just compute each of these individual derivatives and compose them to get what is the overall derivative of the loss function. Similarly, I can also compute the derivative of the loss function with respect to w prime, and that follows these red marked arrows, right. So, essentially this is how the computational graph abstraction is used to specify a neural network for a corresponding deep learning library, and then given suitable implementation of the different propagation passes that will be available in the library, the computation really goes on, right. So, from this point, let us switch to another alternative neural network architecture, which is better known as convolution neural network. Well, this is very similar to normal neural networks that we have already discussed, but they are kind of also specialized, that their architecture is tuned towards image classification tasks. So, what is special about image classification tasks? Let us understand that an input image, when we know that this is an image, it always is going to form a very regular structure. It is going to be a multidimensional matrix, where each of the pixel values are encoded for corresponding to different channel of colors, right. And given that an image has got certain of intrinsic properties, the convolution neural network makes use of those properties to decide its architectural primitives. An end-to-end convolutional neural network will express a simple differentiable score function. It will essentially map the raw image pixels from the input to class scores at the other. So, the class score can be many things, right. So, you are essentially, let us say you are trying to recognize some numerals, right. So, essentially you want this number 4 to be recognized, and you have many output possibilities, 10 digit possibilities. So, the class for the digit 4 should get the highest value, right, and that is how you want this neural network architecture to work and assign the class score, right. But the way it differs is, the CNNs, since they are going to be tuned towards processing images only, they are arranged in some specific ways. For example, when you are capturing an image, typically the arrangement even for a 2D image, your data structure shall be a 3-dimensional thing. Essentially, you should have the pixel values for corresponding to height and width coordinates, and also for each coordinate pair of height and width, you are going to have 3 channels and you have to have memberships for all those 3 color channels, right. So, you have the input standard in available in a 3-dimensional standard, and corresponding to that the CNN will have neurons arranged in 3 dimensions also. And also there is something important, that in general when people dig up CNNs, they also make use of facts like, well, the neural network architecture need not have full connections at every point, like each intermediate node can represent a filter which is tuned towards gathering a specific kind of information, and it may not be gathering it from the all parts of the image but some specific parts of the image and all that. All we are trying to say is that once we decide that the input is an image and these are the features of the image I am looking for, accordingly I can decide weights, and accordingly I can also decide the connectivity of the intermediate nodes. So, holistically speaking, the CNN is typically made of the following layers. You have the input layer. After the input layer, you have this what we call as convolutional layers. So, the convolutional layers represent different image filters available as 3D masks, which will be applied for mining information from the image. And then you have something called the pooling layer. Now, this is followed by an activation layer, typically that is taken as ReLU, and at the end you have what we call as the fully connected layer, which is just like the normal neural networks. The input and output for each of these layers 1 to 4, they represent 3D image volumes. So, up to the ReLU layer, the input is a 3D image. After the convolution operation, I get 3D volumes. After the pooling, I will again get a 3D volume with some reduction in the length, the heights, width, etc. Even after ReLU, I have a 3D volume, but the fully connected layer is used at the end, and the 3D volume is flattened and it is provided as a linearized score, right. So, for example, we will just show some examples here, like which are popularly used data sets. For example, this CIFAR-10 data set, for that I can have a multi-class classification problem which is pretty well known. I have input images of size 32 cross 32. Let us say I am trying to classify these images into these categories provided in the left hand side, and of course, I have 3 channels for red, green and blue, right. So, overall the input each of the input images is of the dimension 3 cross 32 cross 32. So, the convolution layer. So, this is essentially the core building block of a CNN, and this is a computationally expensive layer, and it works on the input images which are 3D image volumes, and essentially there are some convolution masks or filters which operate on these input volumes and provide and as output this layer is going to again produce a 3D volume. Now, the dimension of this output, they are dictated by 3 parameters, that what is the depth of the layer, at what stride it is going to work, and the amount of 0 paddings. We will understand what it means. So, let us take an example of a 3D convolution, but before that let us just understand that how this is again conforming to the basic neural network architecture. So, instead of having inputs like x1, x2, etc., which we are discussing in our earlier things, essentially we were talking about test data or training the training data or the test data, depending on what kind of work you are doing, which were like vectors or matrices or tensors, right. And essentially the image is also following such a representation. For example, on the left hand side we are considering here a 2D image, but the thing is we are operating it with a weight matrix, and it happens to be that in this case the weight matrix is basically an image filter or a mask, right. And the way you choose the mask depends on what kind of operations you want to do on the image, what kind of information you want to take out of the image, right. So, here you have an image, here you have a 2D weight filter mask, let us call it W, because this is essentially like a matrix vector multiplication you are doing, matrix multiplication you are doing, the image is getting transformed with this mask, but the operation you are doing is a bit different from standard matrix multiplication. What you are really doing here is convolution operation, because that is how you operate filters on images. I mean, of course, what is convolution, how exactly we do convolution, I mean, what is the motivation behind doing that. I mean, as we know that these are standard image processing algorithms, and they are standard transformations coming from signals and systems theory, which define that, well, by performing convolution with some specific filter, what information am I really going to get. So, we are really not looking into that, but rather restricting ourselves to understanding that, well, how to implement the convolution. And the important point for us at this point is to understand that here the weights do not do normal matrix multiplication, but rather that gets replaced with the convolution operation, which is the specific feature of convolution neural networks, right. So, how does it really work? For example, if we take this 5 cross 5 image getting convolved with a 3 cross 3 mask, essentially this mask is going to slide over the possible locations on this image and compute an output 2D image like this. Okay. So, let us try and understand how this is going to work. So, maybe we will push in some values here. So, let us take it very simply, let us say it is all ones. So, okay. I am just writing some example values here. Now, when I do the convolution, what is really going to happen is in your output, the value at this location you are getting by applying this input mask on this possible location. So, just overlay this mask over this part of the input image, right, and then you do element wise multiplication. So, what do you really get? So, essentially you are multiplying element wise. So, the values that you are going to get are 0, then 1, then 0, then again 0, 1, 0, then again 0, 1, 0, right. Now, just sum them up. So, you get a 3, right. So, that is what you write here, right. So, is that simple. Now, this gives you the value in the 0, location of the output image. What about the next location? How do you get it? So, again just take the mask and overlay it, but by sliding it one position, right. So, essentially you will be applying the mask on these locations. So, let us say these are my values. So, again you can do the computation now. So, all you get is right. So, sum it up and that is going to give you a 0. So, that is what you get. Similarly, you overlay the mask again here, right. fill up this entry, and then you downshift the mask by one position, fill up this entry, downshift another position, fill up this entry, right shift one position, another position, and downshift like that, right. So, in that way you just compute all the values given this 2D filter, 2D weight filter or the mask, right. So, we can continue like this. So, that is how you can build on this example, and here in this animation we are just trying to show that for the output location how the change of the overlay plays a role when you compute the output values of the image. So, as you can see, you have this 2D input image, you apply the 2D weight filter mask and you are getting a 2D output image. So, there is no change in the dimension, and of course, the dimension of this output image depends on two things: the dimension of the input image as well as the dimension of the mask and in what stride I am applying the operation. We will see what that means. So, then as you can see that for the first location you are putting the mask in the left, top left position that is possible, that is the overlay region. You shift it by one position and you keep on shifting like this in the output image, right. Move to the next row, again keep on shifting in that row, and so on and so forth, right. So, this is how you do the 2D convolution. This is a standard image processing transform. All that is happening is we are now claiming this is getting done in the first layer or any layer which we are defining as a convolution layer of a neural network pipeline. That makes it is a specific pipeline and we call it a convolution neural network. All we are saying that in some of the layers we are not doing a generalized matrix multiplication, we are replacing it by this kind of image filter mask convolution operations to get a different to get a transformed image vector. Fine. Similarly, this idea can hold for even 3D convolutions. So, just like we are considering 2D images and 2D masks, simply consider 3D image and convolving the 3D image. So, this is a convolution we are denoting it here by a 3D weight filter or mask W. So, what will happen here? The operation will slide over the image and compute the neighborhood operation, the weighted sum. So, essentially the weights are getting multiplied with these values in the image that we saw, and then finally we are doing the summation, and then you do it over the elements of I and produce the output image, right. So, essentially you have a 3D input image, a 3D weight filter mask, and the convolution filter will now operation will slide the individual filters over the images, and it will do the neighborhood computation like we discussed earlier already over the elements and produce the output image, right. So, here we are describing it further what really is going on. So, as you can see, these are the on the left hand side we have the image and we are showing the different channels of the image, right. And then I have the 3D masks. So, there are three 2D masks essentially, right. So, that is what we have here, right. This is the convolution operation, and here we are explaining it with a broader diagram. So, essentially you do pairwise convolution for each of the layers, right. So, you have the mask arranged with specific layers for specific image channels, and you just do component wise convolution operation computation. So, this is for the first channel, this is for the second image channel, this is for the third image channel. You are just doing convolution for the corresponding mask layers and doing the operation like we have discussed earlier. You are taking this mask, overlaying it over the image and then sliding it on both ways and computing each of the entries of the output image transformation. And how do you really compute? After overlaying the mask, you are doing element wise multiplication. Essentially, you are multiplying this image pixel information with the mask weights and finally doing a weighted sum of this region, again the weighted sum of the next region, and so on and so forth, right. And finally, you do element wise addition to just flatten these 3D outputs to a 2D image transformed output, right. So, here you are again doing element wise addition, right. So, first you have already done an element wise addition, which was also weighted by the mask for computing each of these entries, and then for these 3 sets of 2D masks you do individual element wise addition to get the values here, 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 so on and so forth, right. Now, let us move forward. So, if we keep on doing it for multiple masks, because here we just considered a 3D image with one 3D mask, but in general in a neural network architecture I can have multiple masks, right. So, this is the 3D image, there is one convolution to be done with one 3D mask, another convolution to be done with another 3D mask, another convolution to be done with another 3D mask. So, as we have seen just in the previous picture, so this convolution is going to provide me with one 2D output, this convolution is going to provide me with another 2D output, and again this convolution is going to provide me with another 2D output, so on and so forth, right. Now, we have already discussed the notion of hyperparameters. For example, for our earlier normal vanilla neural network example, the hyperparameters were the different layers and the different set of the neural network, essentially the architecture of the neural network, the weight matrices and all that. So, we have to also decide what it should be in this case for convolution layer, right. So, with this basic introduction to CNNs, we will end this lecture. Thank you for your attention.